All right, thanks everyone for coming out in a snowstorm to hear about my favorite subject, cosmology. So if you were an astronomer 1,000 years ago, your picture of the universe would look something like this. The Earth is at the center of the universe, followed by the 7 planets, which are the Moon, Mercury, Venus. The 4th planet is, of course, the Sun, then Jupiter, Saturn, and then the firmament, which is a big, opaque, solid sphere surrounding the Earth with little pinpricks, which are the stars. If you were an astronomer 100 years ago, your picture would be very different. Glossing over a lot of history, there followed a sequence of historical developments which slowly took the Earth out of the center of the universe and also made the universe a much larger place. The Earth is one of several planets orbiting the Sun, which is one of many stars in the galaxy, which is one of many galaxies in a very large universe separated by vast amounts of empty space. The 21st century picture of the universe is actually pretty different from this. We know a lot more than we did 100 years ago or even 30 years ago, but the picture is hard to summarize in a picture because it involves a lot of unfamiliar physics concepts. So it'll take some time to explain. In the next hour, I'll summarize our modern understanding of cosmology, which includes not only a new picture of the universe, but also answers to some of the oldest, most self-motivating questions in science, like how did the universe begin, what is it composed of, and how will it end? The talk will have 3 parts. In the first part, I'll talk about the expanding universe. So before I get into the big picture, I want to talk about something specific and technical. You're probably familiar from everyday experience with the Doppler effect for sound waves. A moving source of sound, say a siren on a moving ambulance, if the motion is toward the listener, then the listener will perceive the sound at a higher pitch because the wavefronts bunch up and the apparent wavelength is shorter, or equivalently the apparent frequency is higher. Likewise, a receding source of sound is perceived at a lower pitch. There's also a Doppler effect for light, but you wouldn't be familiar with it unless you're an astronomer. In order for it to be large enough to be noticeable, the speeds involved have to be an appreciable fraction of the speed of light. An object which is moving, say, away from a viewer, emitting light, is seen with the light at a lower frequency, or a redder color, and a source which is emitting light and moving toward an observer is seen with a bluer color. In both the sound and light cases, it's the frequency that's shifted by the relative motion, but frequency of sound is what we perceive as pitch, and frequency of light is what we experience as color. Next, I want to tell you about a revolutionary discovery made by the astronomer Edwin Hubble in 1929. What Hubble was trying to do is what nowadays we would call a redshift survey. So here's the idea. Here's Hubble with his telescope. I have a low-budget way of making slides that involves a lot of Google image search. He looks out and sees a galaxy, and he measures the redshift. Say this one is blue, it has a small blue shift. By the Doppler effect, that can be translated into a measurement of its velocity, since it's blue shifted, in the direction of the Earth by some definite amount, say 100 kilometers per second. Here's another one, it's red. And the redshift can be measured and translated to some recessional velocity, say 200 kilometers per second. The Doppler shift can be measured very accurately using spectrographs. And so we can measure very accurately the component of the velocity which is either toward us or away from us. The tangential or side-to-side component of the velocity, by the way, is much harder to measure, but we can get an incomplete picture, a partial picture, of how the galaxies are moving around relative to each other. So this is what Hubble was trying to do. That was the idea of his redshift survey. And when Hubble made his observations, here's what he found. Nearby galaxies are equally likely to be blue-shifted or red-shifted, i.e. moving toward us or away from us. But as you go further out, there's a statistical tendency for galaxies to be redshifted, which increases, and the characteristic redshifts get larger as you go further away. Now, this was a total shock and difficult to interpret. It's as if we sit in the center of the universe, and all the galaxies in the universe are receding away from us by a velocity of recession that just gets larger and larger as we go further away. Now, Hubble didn't know it at the time, but the physics theoretical framework for interpreting his observations had been put forward a few years before. In 1915, Einstein proposed his general theory of relativity, according to which distances and times are dynamical quantities. I'll explain shortly exactly what that means. and he proposed a set of equations for predicting in various circumstances how those dynamical distances and times would evolve with time. When Einstein's equations are applied to the universe as a whole, they predict an expanding universe. Now, Einstein famously regarded this as a failure of his theory and even tried to doctor up his own equations to get rid of this prediction. And it took these physicists, Friedmann, a Russian physicist who was the first, but died shortly after publishing his work, and this Belgian astronomer and priest, you can see he's got a robe in the picture, Lemaitre, who I think would be the first guy that really had the full modern picture of the expanding universe. He even originated the Big Bang Theory, although he called it the cosmic egg theory, which is an even more fun name. So here's what relativity predicts. Here's what the expanding universe means. Consider a hypothetical universe, the grid universe, in which all galaxies happen to sit at the vertices of a regular grid with some regular spacing of, say, 1 million light years, and are at rest. In this grid universe, even though the galaxies are pulling on each other gravitationally, there's no net motion in any particular direction because of the symmetry of this situation. This galaxy is pulled on equally hard by all of its neighbors, and so it doesn't move. Likewise for every other galaxy. And so you might think that the grid universe is a rather boring, static place. But in general relativity, there is one thing that happens, which is that if we measure the spacing of the grid at some later time, say 10 billion years later, the spacing will have increased to, say, 2 million light years. So if we just wait and take a ruler and measure, we get a different number. That's what we mean when we say the universe is expanding. Why does it expand? Well, general relativity is a proposal that distances are dynamical quantities that change, and a set of equations for predicting how they change. And the test of whether that idea is correct is whether it agrees with experiments. Now, a point I want to emphasize is that, let me go back. The point that I want to emphasize is that there's no center to the expansion. If you consider how the expanding universe would look by an observer living in this galaxy, they see the distance to the neighboring galaxy increasing with time. So with the numbers from the previous slides, by, say, 1 million light years every 10 billion years, so some definite velocity, and a galaxy that was 2 positions over on the grid would be increasing at twice that velocity, and so on. So viewed from the perspective of any galaxy in the grid, it looks like you sit at the center of the universe with the other galaxies moving away from you. But there's no center to the expansion. What the expanding universe means is that the distance between any 2 points in the universe is just increasing with time. It's space itself that's expanding. And that statement can be made without reference to any particular center. So this galaxy, if they observe, they'll see exactly the same picture. Now, Hubble's observations are nearly the same universe. The only difference is that, of course, in the real universe, the galaxies don't live on the vertices of a regular grid, and there's also some random scatter on top of the uniform recession because the galaxies move around, and say maybe this pair of galaxies is a binary system, they're orbiting each other, and this galaxy just happens to be moving toward us, and this galaxy just happens to be moving away from us, and those so-called peculiar velocities add random scatter to the recession. But if we look far enough away, they average down, and we see the overall recession. So this is a beautiful example in the history of physics of the intersection between theory and experiment. Einstein's theory made a very counterintuitive prediction, the prediction of an expanding universe. Hubble's experiment made a counterintuitive observation, and it turned out that the two linked together. Hubble's observations were strong evidence in support of Einstein's theory. And Einstein's theory explains this counterintuitive picture that Hubble saw. In the next part of the talk, I'll talk about the cosmic microwave background. In the years following Hubble's discovery, physicists had a lot of time to think about the implications of an expanding universe without having a lot of new observational input. As you'll see, if the idea of an expanding universe is taken to its logical conclusion, one can make some truly remarkable predictions. If you imagine running the clock backward in an expanding universe, what that would mean is that as you run the clock backward, the distance between any two galaxies, say, is decreasing with time. You can run the clock back to a time when the distance between galaxies was equal to, say, the size of a galaxy itself, so they'd be touching, or 1/100th the size, so they would be 99% overlapping. At minimum, what this tells you is that the universe must have been very different in the far past than it appears today, where, say, the stars in the universe are separated out into widely spaced discrete galaxies. In fact, if you do the math, the equations of general relativity predict a disaster. All distances go to zero a finite time in the past. So there's some finite time in the past, which we now know to be about 14 billion years, when if you just run the equations of general relativity backward in time, you would predict that the distance between any 2 points is zero, and everything is on top of everything else. Now, at various points in the history of physics when equations have predicted nonsense, that's always been a sign that our understanding is incomplete, and there are laws of physics we don't know about yet. And so the proper interpretation of this Big Bang situation, is just that our understanding is incomplete, and we can't make predictions arbitrarily far into the past. It's not a prediction for any specific dramatic event that took place in the early universe. Another implication, we'll come back to this later, another implication of the expanding universe is that we don't live in a special place in the universe, but we do live in a special place in time. The ancient astronomers believed that the Earth was at the center of the universe, and it was actually a revolutionary discovery to learn otherwise. In the expanding universe, it's also true that we don't sit at the center. There's no special place. Any 2 points in the expanding universe are equivalent. But the universe does evolve with time, and we do live at a special time between an early time where the universe was very small and looked very different from how it does today, and a late time when everything will be expanded very far away from everything else, and the material to form new stars is extinguished. So this statement is also, I think, a revolutionary discovery and a new picture. In fact, the evolution with modern data, which is much more powerful than what Hubble had, the evolution of the universe can be seen directly. Here's a map of galaxies in the universe from a modern telescope, the Sloan Digital Sky Survey. The Earth is at the center, and we can observe out to billions of light years away. The reason there's a cone geometry here, by the way, is that this experiment only measures part of the sky. If it mapped the whole sky, it would be like a circle. A very important note on this picture. Because we can see billions of light years away, we also get to look backward in time. If we observe a galaxy which is, say, 2 billion light years away, we don't see the galaxy as it is now. We see it as it was 2 billion years ago, because that's how long it took the light to get to us. So you get to experience a form of time travel, whereas you look farther and farther out into the universe, you get to see the universe as it was longer and longer in the past. That's an important thing to remember. I'm going to show a lot of plots like this, and I've gotten so used to this idea that I tend to just automatically think of this axis interchangeably as either a distance that you're looking out or a time that you're looking back into the past. Anyway, you can see in data sets like this directly that the universe is evolving. If you look far enough away or equivalently far enough back, then you can see the characteristic properties of the galaxies, their sizes, shapes, rates of star formation, and so on changing. The idea that by looking far away we can look backward in time is a very powerful one in cosmology. In fact, I'll explain soon that there's a way we can look back almost all the way to the Big Bang. Now, a concept that I'll talk about a lot is gravitational instability. This is just the idea that because gravity is an attractive force, it always makes the universe more structured with time. This is a computer simulation of gravitational instability operating in a cloud of gas. Initially, the only structure in this gas is that there are it's almost featureless, almost structureless, but there are little regions where it's, say, 1% more dense than average or 1% less dense than average. Now, what will happen is that a little region, which is 1% more dense than average, will gravitate more strongly than its neighbors and will tend to pull gas in. This leads to a situation where the little region is 2% more dense than average, 3%, and so on, and the initial structure gets magnified by gravity. So when I start the movie, the first thing that you'll see happen is that the gas is rapidly pulled into the initial overdense regions and little filaments connecting those regions. Gravity next tries to structure things further by collapsing all the filaments together into a little sheet. And then as you watch, you can see a little point-like structure start to develop in the center here. This structure is getting larger because it's fed by inflows from the sheet. This is sort of a detail, but you can see it start to rotate. That happens because centrifugal force from the rotation needs to balance out the gravitational infall. As the structure develops, you can see that by the end of the simulation, what we have is a new rapidly rotating galaxy, which is formed out of the gas cloud. So gravitational instability can convert a cloud of gas with almost no structure into something as structured as a galaxy. The same principle is true on larger scales. Here's a computer simulation of a region of the universe which is several million light years in size, starting about 50 million years after the Big Bang. We now believe with modern data, and I'll say later how we know this, that the early universe, 50 million years after the Big Bang, contains almost no initial structure. So the only sense in which this gas is structured is that there are variations in density on the order of 1% from one place to another. When I start the movie, not much happens at first, but the initial structure is slowly growing by gravitational instability. The motion that you see here, by the way, is the camera moving, not that gas moving. With time, the gas collects into filaments, and you can see galaxies start to form. This is on a much larger scale, so the galaxies are much smaller than the simulation box. The next level of structure which develops is that the galaxies start to merge together. If you look closely, you can see in the filaments the galaxies moving together. Large galaxies are formed through a process of gravitational instability, where small ones merge together mostly along filaments to make large ones. This structure of filaments, by the way, is called the cosmic web. And so on the largest scales of the universe, we can convert a nearly structureless universe into the rich array of galaxies and structure that we see today. Now this cone is showing the evolution of the universe by gravitational instability over time. The cone shape is supposed to remind you that the universe is expanding. I want to talk about the dark ages, which is the initial period before the formation of stars and galaxies, when the universe is full of a nearly uniform gas, which is slowly growing structure through gravitational collapse. Now, a property of a gas in an expanding universe is that as the universe expands, the gas cools. You've experienced a version of this if you've felt the cold air from an aerosol can. Gas in the can is under pressure, so when you release it, it expands, and gases cool when they expand. The same is true when the universe expands. So if at a certain time, say 10 million years after the Big Bang, the gas filling the universe has a temperature of, say, 80 Celsius, then if we run the clock backwards, you'll see in a sec why I want to run it backwards, then 5 million years after the Big Bang, it would be at a higher temperature, 300 Celsius, 1500 Celsius, and so on. When we reach a critical temperature, namely 3000 Celsius, something interesting happens. The gas dissociates into a plasma. When I say gas, what I mean is a gas made of atoms, i.e. Electrons bound to nuclei. And a plasma is just a different kind of gas, really, where the electrons are so hot that they've dissociated from the nuclei, and you just have a gas of the constituent unbound nuclei and electrons. The sun is an example of a plasma. Almost all the material in the sun is in this plasma state. So we can predict that early in the universe's history, the age where this happens is about 400,000 years after the Big Bang, that the universe was full of matter in its plasma state, not a gas. Now, one thing that's interesting about a plasma is that it's opaque, unlike a gas, which is transparent, suggesting the possibility that we could look back and see it. So if we could look far enough, we might see something like this. Close to us, we have the galaxies. If we look out a little further, we see the dark ages. And then we should see a wall. If this picture is correct, we should literally see a wall encircling the Earth of opaque plasma. You can see how far one can go just by following the implications of the expanding universe to their logical conclusion, running back the clock. To look for the plasma in the sky, we need to know what color it is. Of course, I mean color in the astronomer's sense, where we think about the whole electromagnetic spectrum, of which our visible set of colors is a narrow subset. Because we know the temperature of the plasma, we know we're looking for the plasma surface at a temperature of 3,000 Celsius. It's possible to calculate from atomic physics what color we would expect to see. And when you do this, you get a color that turns out to be in the short wave infrared part of the spectrum, a little bit redder than visible. But because this light was emitted a long time ago, there's a very large Doppler redshift, so that that same light observed now should be in the microwave part of the spectrum. So we're looking for a big microwave-colored wall very far away in space, way past the galaxies and everything else. The light that I'm talking about has a name. It's called the cosmic microwave background. And it was observed in 1965 by these guys, Penzias and Wilson. So these guys were non-physicists. They were radio engineers. They were doing some communications work, and they found the cosmic microwave background by accident. They had built this big antenna, and they discovered that they were getting a signal no matter what they did, whether it was day or night, wherever they pointed it on the sky. These guys, I think, get kind of sometimes a bad rap in the history books because they found something, really fantastic, but they found it sort of by accident. But I think it's kind of to their credit if you read their account. The tremendous care that they took in ruling out alternative explanations until they were forced to conclude that the sky was bright everywhere in microwaves. For a while, they had like a bird poop theory that their signal was due to birds pooping in this thing, and they cleaned it out carefully and bought shotguns and ran the birds off. It's really entertaining to read their account. Anyway, when all was said and done, they had discovered the following. If I were to show you an image of the sky at visible wavelengths of light, this would look sort of familiar. You can see bright stars. This is the plane of our galaxy. This is the Milky Way. The galactic center here is bright. There's some dust clouds that are obscuring things in different places. If your eyes could see in the microwave part of the spectrum, then you would see this sky. It's light all the time and featureless. Most of the light in the universe, by the way, is in the microwave. In a statistical sense, the universe is microwave colored. And what you're seeing is you're looking all the way back to the wall of plasma surrounding the Earth from when the universe was only 400,000 years old. Now, we can't see any further than this because the plasma is opaque. But if we could, what would you see? Well, the surface of the plasma is 3,000 Celsius. And if we look further back, we're looking a little bit further back in time. The temperature goes up as you go backward in time. So a little bit further back, there would be a plasma that was 4,000 Celsius, 5,000, and so on. And in fact, when you do the calculation, you find that you reach infinite temperature a finite distance away. This is the Big Bang problem that we found before. The distance is actually very close to the plasma surface itself. So if you could look just a little bit further, you would reach a point where the plasma had a predicted infinite temperature. What that, of course, really means is that our predictivity has failed. We don't know the correct laws of physics that would allow us to predict what you would see if you could look a little bit further. But you can't because the surface is opaque and blocks out the light. But if you could, we're very close to reaching disaster. Now I want to pause and make a few comments on this picture, which are very important. I found that when I teach cosmology to people who are still learning, there's a few potential misunderstandings in this picture, which always cause confusion later. So one comment is that it looks like the Earth is at the center here, and that the character of the universe is changing as you go from place to place. What's really happening is that the universe is the same everywhere, but you're looking back in time. So it's not that you're looking out in space to a place where the universe is different. It's just that you're looking back in time to a time when the universe was a plasma. If you were to take a snapshot of the whole universe today, it would all look the same. It would all be full of galaxies out to the edges of the figure. If you were to take a snapshot of the universe take a snapshot of the whole universe at the same time, during the Dark Ages, it would all look dark. And during the time when the universe was a plasma, the whole universe would look like a uniform plasma. So there's no preferred center, and an observer that was sitting here, for example, would see the same picture just shifted over so that it's centered at their location. Another thing that is suggested by this plot is that the universe is somehow finite. And that is true in a practical observational sense. The furthest away that we can ever look, at least with light, is to this plasma surface. And in fact, if we could look a little bit farther, we would really get into trouble. Our equations wouldn't predict what we could see anymore. So there's a finite amount that we can ever observe. But as far as we know, the universe is infinite. Or at least it's so large we can't distinguish it observationally from an infinite universe. We believe that if you could take a snapshot today and keep going, it would look the same well past the edges of the screen. Okay, so this is a picture of the expanding universe. Now I'm going to show you some modern measurements of the cosmic microwave background. So these images are all from two very influential satellite experiments, the WMAP satellite, which is a NASA-led mission, and the Planck satellite, which is a European ESA mission. I've been fortunate enough to take part in both of these experiments. So the way these experiments work is that the satellite goes out. It takes about 6 months to travel very far from the Earth so that it's in a very stable thermal environment and cool down to reach a nice state of thermal equilibrium. And then it has a beam that scans the sky with very sensitive detectors. When this is done, what's revealed is that the microwave background isn't perfectly uniform, as I showed at all, but contains features at very low contrast. These features are measured across the whole sky, and we make a map of the microwave sky zoomed in to very high contrast, which looks like this. Now this is what the raw data looks like from the instrument. This is mostly what you're seeing here is dust emission in the microwave part of the spectrum, but from our galaxy. If we separate that out, if we subtract the contribution from our galaxy, which we can do because dust and the cosmic microwave background, the light from the plasma surface, have different frequency dependence or colors, then you get a picture like this, which represents the thermal state of the plasma surface itself. What this means is that the plasma surface has regions which are slightly hotter, where the radiation is slightly more intense, and regions where the radiation is slightly less intense. These are very low contrast features. The difference between the intensity in the hottest point in the map and the coldest point in the map, they differ only at the 4th decimal place. So earlier I said that the universe starts out with almost no structure, and the way we know that's true is because we can take this snapshot of the universe 100,000 years after the Big Bang, when the universe is a plasma, and we see that conditions from place to place in the universe only differ in the 4th decimal place. So if you were around in the early universe, you would live in a nearly uniform hot plasma with almost no structure. The only sense in which there's structure is that if you traveled tens of millions of light years away, you would see a plasma with a temperature that was slightly different in the 4th decimal place. Now the modern theory of how we get from then to now works like this. The first thing that happens is that the plasma cools down to a gas, and the universe becomes transparent. And then gravitational instability starts to work its magic and magnify tiny structures that were present in the plasma. We go through the dark ages and the first stars form, and then the cosmic web and the galaxies. So a tiny feature in the cosmic microwave background, what looks like a tiny spot in one of these microwave background maps, might be the seed for, say, a cluster of galaxies today, after gravitational instability happens. But the real power of the cosmic microwave background, the real excitement, is that we can do a kind of cosmic fingerprinting. So the statistics of the spots in the CMB are very sensitive to the characteristic properties of the universe, so they can be a cosmic fingerprint that identifies our universe out of many theoretical possibilities. So let me give you an example. How old is the universe? This, I think, is a very natural question to ask. Hubble tried to measure the age of the universe and got 2 billion years. Einstein, very famously, was very attached to the idea that the universe was infinitely old. Of course, philosophers and in religion, there's been a lot of speculation on this question. So it's amazing. I find it truly amazing that with modern CMB data, we can make the following statement. With 95% statistical confidence, the age of the universe is greater than 13.68 billion years and less than 13.92 billion years. Now, I want to give you some idea of how this analysis is actually done. So the next few slides are going to be a little technical, but when I say that this number or that number, like the age of the universe, is measured from the CMB, I want to give some idea of how we actually conduct that measurement. So I want to start with this analogy. You've probably seen spectral analysis of sound in graphic equalizer format. So this range represents the range of frequencies or pitches which is hearable by the human ear, with the low end or bass on the right and the high or treble end, the lower bass end on the left and the higher treble end on the right. And now if I play a low tone, that shows up mainly on the low end of the spectrum. If I play a middle tone, you can see a single peak in the middle. And if I play a natural tone, like a violin, that might have multiple peaks or some interesting shape in its constituent frequencies that tells you something about the instrument that made it. We can do an analogous sort of spectral analysis of the hot and cold spots in the cosmic microwave background. Here, what the axis means, the axis corresponds to features in this map of different apparent size in degrees. So we go through the map, well, a computer goes through the map, and says, here's a feature that's 1 degree in size, I'll put it down here. Here's a feature that's 1/10 of a degree in size, I'll put it out here. And then we add them all up and get this rather interesting curve. And if I had more time, I'd love to tell you about the plasma physics that generates this shape. That shows that, for example, that there are a lot of features at about a degree, fewer features at this scale, which is, say, 1/2 a degree, and so on. So this analysis distills the information in this map down into a curve. Now we can predict this curve. So the curve that I showed you, by the way, was actually a fit to modern measurements of the cosmic microwave background, not the measurements themselves. But the accuracy of the measurements is comparable to the thickness of the line, so it wouldn't really look that different if I showed you the measurements. We can calculate this curve, and it depends on the age of the universe. If we use the universe with age 14.8 billion years instead of 13.8 billion years, we would get a different curve that disagrees with the measurements. So in this way, we can measure with statistical errors the age of the universe and other characteristic properties, the composition, the total star formation that's happened in our universe, and so on. When we do this, we find that there are some things that are unsurprising. Like, there's nothing particularly surprising a priori about this number. But we also find that there are basic aspects of our universe that were total surprises when discovered that we don't fully understand. And this is what I want to tell you in the last part of the talk. So far I've been telling you about things that we understand pretty well. And now I want to tell you about some surprises that we've uncovered that we don't fully understand yet. So I would say that, broadly speaking, almost every cosmologist is thinking about one of 3 fundamental mysteries. What is dark matter? What is dark energy? And what is the physics of the very beginning? So I'm going to tell you about each of these. Starting with dark matter. So as you know, ordinary matter is made of protons, neutrons, and electrons. Surprisingly, we have learned that the universe at large is mostly made of something else. There's about 5 times more dark matter in the universe than the ordinary proton, neutron, electron-based matter that we're familiar with. Now, it would be natural to follow this sentence by a statement about what dark matter is. I can't do that because no one knows, but I can tell you the properties that we do know. First off, it doesn't absorb, reflect, or emit light. It has no interaction with light. So a better name than dark matter, actually, I think a more illustrative name would be transparent matter. That's the proper term for matter that doesn't interact with light. It doesn't interact with ordinary matter. It just goes right through it. There are dark matter particles streaming through this room right now, through the walls, through the Earth. What it does do, the way that we can know it's there, is it gravitates. So ordinary matter and dark matter attract each other and themselves gravitationally, so we can observe dark matter through its indirect effect on ordinary luminous matter that we see directly. Dark matter has a large effect, for example, on the formation of galaxies. Here's a computer simulation of a cluster of galaxies. Red is dark matter, white is ordinary matter. You can see that the dark matter, gravitational instability has aggregated the dark matter into little blobs, which we call dark matter halos, and the galaxies are smaller objects that live inside those halos. In fact, the dark matter halos form first and create the proper conditions for galaxies to form. So dark matter plays a very crucial role by forming halos in the modern theory of galaxy formation. Now, if you're a skeptical person like me, you're probably thinking this is a lot to swallow. How do we really know that the universe is full of invisible dark matter that we can't see directly? Well, the first observational evidence came from observations of rotations of galaxies. So the rate at which different parts of a galaxy rotate is related to the distribution of matter in the galaxy. So if we assume that the matter in the stars of the galaxy was all that there was, then we would predict a certain type of rotation, shown here on the left, where the arms of the galaxy rotate relatively slowly and the center rotates quickly, because there's not much matter out here in the arms. But if the galaxy sits in a dark matter halo, then there's matter everywhere, and the halo is heavier than the galaxy itself. So the matter is roughly uniformly distributed, and the arms rotate quickly, as does the center. And this matches what's actually observed. Now, I would say that on its own, this is fairly inconclusive evidence for dark matter. I'm not sure that if I had been around in 1970 when this was first being discussed, I would have found this hypothesis, the dark matter hypothesis, fully convincing. One could imagine alternative hypotheses, like maybe the outer parts of the galaxy are just full of gas that for some reason hasn't formed stars yet, but is still contributing to the mass. But what happened is that when the dark matter hypothesis was formulated, astronomers found that it explained a lot of different types of observations. For example, nowadays we have really overwhelming evidence. The cosmic microwave background power spectrum, the standard prediction, which agrees with the data, is calculated assuming about 5 times more dark matter than ordinary matter. And I tried just for fun to see how well I could do at matching it without including dark matter in the calculation. And this is the best I could do. It's wildly different. It's a very, an overwhelmingly poor fit to the data. There are many other lines of evidence nowadays. The shapes and sizes of galaxies that we see, we wouldn't be able to get the galaxy formation right, and so on. Nowadays, about 10 different types of evidence, lines of evidence, that are all simultaneously explained by the dark matter hypothesis. So this is the hallmark of a successful theory, that a simple hypothesis proposed to explain one thing, rotation rates of galaxies, actually explains a lot of unrelated phenomena. And this has convinced almost every cosmologist, including me, that the dark matter hypothesis has to be correct. But we don't know what dark matter is on a microscopic level. We've never been able to make it in the lab or a particle accelerator. So its existence is kind of a fundamental puzzle. Next, I want to talk about dark energy. So even though the names dark matter and dark energy are very similar, they actually refer to 2 quite distinct phenomena. So dark energy refers to the following phenomenon. Einstein's theory of relativity makes a prediction for the expansion rate of the universe as a function of time. And what it predicts is a slowing expansion, as shown in the bottom part of the plot. When we measure the expansion rate with time, what we find is that it agrees pretty well with the prediction. It agrees well with the prediction of Einstein's relativity for the first 8 billion years or so, and then it switches over at recent times to a totally different accelerating type of expansion. So dark energy is a catch-all term for whatever unknown physics is causing the measured expansion of the universe to deviate from the prediction. Now, Now, one explanation that's been put forward, and this I would say is sort of the orthodox front-runner explanation, but it's by no means established conclusively, is that if you were to modify Einstein's theory of gravity by allowing the vacuum, for empty space itself, to have a slightly non-zero energy density that is included as a source in Einstein's equations to drive the expansion of the universe. So you say the universe expands as if the vacuum itself were full of a very tiny but non-zero distribution of matter. The difference between this explanation, the vacuum energy density being non-zero, and the universe being full of, say, dark matter, is that dark matter dilutes with time. As the universe expands, the dark matter particles get farther and farther away from each other and dilute. But if the vacuum is assumed to have a non-zero energy density, then as the universe expands, you just generate more and more vacuum. So this is why we see this, this effect small for a while, but then take over at recent times when the universe gets big enough. So that's one possibility. And this theory predicts a specific dependence of the expansion rate with time, which is roughly what we see in the data, but the data is not great. So this is not established. This explanation is consistent with the data, but I would not say that the data is good enough that it's conclusive. And then there are many other possibilities. One thing that may be happening is that maybe our theory of gravity is incomplete. I mean, Einstein's theory of gravity made a prediction, and we measure something different. Maybe that just means that the theory of gravity is just, this is telling us that Einstein's theory of gravity is incomplete in some more fundamental way that we haven't quite been able to think of yet. Or maybe there's another source of gravitation in the universe that we don't quite understand yet. It would have to be something kind of exotic, like a fluid with negative pressure, but something like that might work. A natural question to ask is, how will the universe end? Dark energy qualitatively changes that answer. Since we live in a universe where an accelerating expansion is suddenly taking over, if you extrapolate our universe far into the future, what will happen is you just get a more and more rapid expansion, an exponential expansion, in fact, so that if you wait 10 billion years, every galaxy is twice as far from us as it was today, another 10 billion years, 4 times as far, and so on. So the universe just dilutes with galaxies with time, the CMB dims out, and eventually you live in kind of a cold, lonely universe where you have no neighbors. That's our current extrapolation of what we measure. A little depressing. Another natural question to ask is, what is the universe composed of? So the dark matter and dark energy phenomena show a very surprising answer to this question. There's more dark matter in the universe than there is ordinary matter, and at least if the cosmological constant is correct, the explanation is correct, what dark energy means is that there's a bunch of density, matter, or equivalently energy in the universe associated with the vacuum that represents an even larger fraction. So the ordinary matter that we're familiar with, that make up the Earth, the Sun, and so on, is only 5% of the total composition of the universe, which is sort of a shocking statement. So we don't live in a special place in the universe. We do live in a special place in time. And I think more profoundly, the stuff that we're familiar with, the matter that we're familiar with, is not representative of the universe at large. Statistically speaking, most of the universe is made of something else. That's kind of a surprising thing to find. Next, I want to talk about something which I personally just find incredibly interesting. This is like my favorite topic, the physics of the very beginning. Our universe has a Big Bang. What that means is that if we looked out, we would expect to see a plasma with higher and higher temperatures until we reached an infinite temperature at a finite radius, and we do not know the laws of physics to keep predicting. So we'd like to understand what's happening here, properly understand the Big Bang, and fill in the question marks. Now, if the surface of the plasma is a 3,000 degree plasma, which is sort of like the conditions of a star, then if you imagine going out so that you go to higher and higher temperature, eventually you reach a situation where the temperature is so high, say trillions of degrees, that the particles in the plasma are crashing together at very high energy. Now, there's a principle in physics that as you go to higher and higher energies, new types of particles are created and new types of physics emerge. Like you've probably heard about particle accelerator experiments, like the Large Hadron Collider. The idea is you just smash stuff together at higher and higher energies and new interesting stuff comes out. So the problem that we're trying to solve here of understanding the Big Bang may be because as we go back, the universe becomes more and more like a giant particle accelerator. May be fundamentally the same problem that particle physicists are trying to solve. What is the physics? What are the laws of physics at very high energies? And so the answer may have something to do with new particles or forces that we don't know about yet. Another possible clue comes from statistical study of the features in the cosmic microwave background. It turns out that the statistics of the hot and cold spots at, say, this part of the plasma surface are correlated to the features over here. In other words, the distribution of features here, for those features to arrange themselves, they would have to know what the features over here were doing. Since these points are separated by tremendous distances in space, this suggests some sort of common origin to all of the perturbations in the universe. It's as if some, omnipotent agent with access to information about what the perturbations in different parts of the universe was doing was responsible for setting the initial conditions. There are also some more technical clues that result from statistical analysis of these fluctuations, like the temperature values fit a bell curve very precisely to a fraction of a percent when plotted. Now, for a long time, we had no successful theory that would explain these features. But in 1982, there was a breakthrough. A remarkable theory was proposed, inflation, which explains all of the statements that I just made. So the way inflation works is like this. Suppose that the early universe is full of one or more new types of particle, and if these new types of particles satisfy certain conditions, they will drive a phase of exponential expansion in the early universe. So after some amount of time, which the times that people talk about are very small, like 10 to the minus 40 seconds, the universe doubles in size after the same amount of time, 4 times the size, 8 times the size, and so on. Then a remarkable thing happens in an exponentially expanding universe. Particles are produced by a quantum mechanical mechanism. Generally speaking, in quantum mechanics, there are processes where two particles, in quantum mechanics, you're allowed to produce two particles out of the vacuum from empty space. Now, normally what happens is that the two particles quickly reannihilate so that the books are balanced, so to speak, and no net particles are produced. But we do know, in order to explain, for example, very accurate measurements of spectral lines of atoms in very accurate quantum mechanical calculations, you do need to include these sort of processes. So we know that they happen. If you calculate what happens in this exponentially expanding universe, what can happen is that a particle pair gets created, but then this very rapid exponential expansion carries the two particles very far away from each other so that they can't find each other again to reannihilate. So quantum mechanics in this rapidly exponentially expanding universe randomly creates particles, and in fact can generate fluctuations out of empty space. Because this process of particle creation is a random process, there'll be random fluctuations in the amount of particles that are produced here versus here. So this can explain how the initial hot and cold spots in the cosmic microwave background are created. Gravitational instability can transform the initial hot and cold spots in the plasma into the structures that we see today, but out of gravitational instability, you can't get something from nothing. If I started with no fluctuations, gravitational instability would never generate them. But in quantum mechanics, you can get something from nothing. By this mechanism, you can start with an empty universe, if it's exponentially expanding, and produce random fluctuations. And the miracle of this theory, inflation, is that when you do the calculations, you find exactly the right statistical properties that we see in the CMB. The correlation that I talked about between different parts of the plasma surface, the bell curve, and so on, can all be matched to within the accuracy of the observations. So if inflation is correct, here's the picture. The circle that we drew as the Big Bang before represents the point in time where the universe made a transition from a quantum mechanical, exponentially expanding universe to a hot plasma. Before this, so something does happen there, but it's not a disaster. The laws of physics are not breaking down. Before that, we just had an exponentially expanding quantum mechanical universe where particles were constantly being produced, creating the initial fluctuations. So this is a totally amazing theory. Before 1982, we didn't have anything like this. In 1982, we had a theory that worked. Here's the problem. That since then, we've found many more theories that also do the job. So maybe it's not such a miracle that inflation works, but some sort of general feature that can happen in many different ways. What's true in all of these theories is that this circle, this point in time, represents some sort of transition from a quantum mechanical universe to a hot plasma. And before this, you had a universe that was quantum mechanical in nature and very different. So the problem that we're trying to solve now is to move forward and discriminate between these different possibilities. And in order to do that, we need more clues from observations. So here's a particular type of observation that has been in the news recently. So some flavors of inflation make the following prediction. During the inflationary universe, in addition to hot and cold spots in the plasma being created, a random background of gravity waves was also created. So gravity waves are propagating disturbances in space-time that are predicted by Einstein's theory of general relativity, or at least it predicts that such a disturbance is possible. And we can look for these in the cosmic microwave background. We can look for them even though they were generated before the plasma surface. The plasma surface is opaque to light, so we can't look further, but a gravity wave goes right through. The plasma is perfectly transparent to gravity waves. So if this signal exists, there's the possibility of looking all the way back through the plasma surface and seeing a signal that originated during the Big Bang itself that is propagated relatively undisturbed until today. So this would be truly amazing to see. It would be truly amazing to predict this thing and see it in the sky today. In March 2014, an analysis of current data in cosmology suggested that the signal had been detected. But if you follow the story, over time, well, by May, some loopholes had been found in this argument, and the answer was maybe. And then on January 30th, which was 5 days ago, the answer was conclusively determined to be no. So this is our current best understanding, our current understanding of combined data of the cosmic microwave background from several sources. And of course, what's really exciting about this for a researcher is that this is all happening right now. So we've gone from, at the beginning of the talk, 1929 to 5 days ago. The exciting thing is that the observations are getting much better, and we're constantly getting new data, and the picture is constantly evolving with time. So I want to tell you about a particularly exciting project that I'm involved in right here in Canada. So the project is called CHIME. It's the first Canadian research telescope in more than 30 years. And it's in Penticton, BC, which is just underneath the sockeye salmon. CHIME is this pair of telescopes in front. The guy in back is a different project. These are radio telescopes. They look for light at radio wavelengths. This mesh has a spacing which is much smaller than the wavelength of radio waves. So the radio waves bounce off as if it was a solid surface and collect. They're focused by the telescope up into this feed line, which is instrumented with a series of antennas. The antennas are connected to some incredibly powerful back-end electronics. So this little electronics house in Penticton, BC, by the time the project is finished, will be one of the most powerful supercomputers in the world, and will process data at a total bandwidth equivalent to a large telecommunications network. And what we're looking for is the following. So it turns out that the dark ages are not completely dark. The hydrogen that fills the universe during the dark ages is faintly emitting radio waves. So we could coin the term almost dark ages, which is not a standard term. to refer to the situation where there's just very faint emission from the neutral hydrogen filling the universe. We're trying to measure this radiation. CHIME is looking sort of here, right at the edge of where the galaxies start to fizzle out and the dark ages start. What we'd eventually like to do is map out all of the dark ages. And this won't be possible with CHIME alone. We'll need many generations of experiments. CHIME is just the first step. But if we could do it, then the total statistical power of all of these fluctuations is much greater than the total statistical power in the cosmic microwave background, which is living here on the plasma surface. That's sort of true because there's much more information in a 3D field than a 2D field. So if we could make this measurement in the future, in the far future, we may be able to massively improve our current picture of cosmology. We're still a long way today, I would say, from the ultimate limits of what we might hope to measure someday. Okay, so to summarize, we live in an expanding universe full of strange stuff. Even the matter that we're composed of is not representative of the universe at large. We don't live in a special place in space, but we do live in a special place in time, midway between the Big Bang, when the universe is a plasma, and when the universe is eventually just exponentially diluted by dark energy. There's some things we understand and some things we don't. If we postulate certain ingredients, dark matter, dark energy, and a quantum mechanical Big Bang, then starting from those postulates, we can understand the observations that we currently see, but we don't understand these ingredients at a fundamental level. We don't know what dark matter is or dark energy conclusively, and there are many possibilities for what may have been happening around the Big Bang. What's really exciting is that we're living in a time where all of the experiments are improving incredibly fast, and it's really exciting to be part of such a fast-paced field. So if 1,000 years ago your picture of the universe looked like this, and 100 years ago it looked like this, then now this is the modern picture, and now you know what it means. It's a much stranger place, I would say, than the picture from 100 years ago, and we're still trying to understand it. The current state of the field is an avalanche of new data and theoretical ideas aimed at understanding the puzzles that we see here. And if I give this talk again in another 20 or 30 years, our picture may be totally different. Thanks.